We sent a spacecraft to the edge of our solar system. It traveled for 9 years. It crossed 4 billion miles of empty, freezing, silent space. And when it finally arrived, it had exactly a few hours. A few hours to do everything, photograph everything, measure everything, and then it was gone, past the target, forever. And that is not even the hardest part of this story. Hey, before we go any further, drop a comment right now. Where in the world are you watching this from? I genuinely want to know. Now stay with me, because what I am about to show you will completely change how you see space travel. Let's rewind, because to understand why reaching another star is almost impossible, you first have to understand why reaching Pluto, something inside our own solar system, is already absurdly, almost comically difficult. Pluto sits roughly 3.67 billion miles from the Sun. Say that number out loud, 3.67 billion miles. For comparison, the Moon is about 239,000 miles away. Mars, at its closest, is around 34 million miles. Pluto is not in the same conversation. Pluto is in a different universe of distance. Now, here's the first trap people fall into. They think the problem is just distance, just space you have to cross. But distance is actually the second problem. The first problem is speed, and the math behind speed will make your head spin. To get to Pluto before you die of old age, you need to leave Earth fast, brutally fast. When New Horizons launched in 2006, it left Earth at 36,000 miles per hour. That is New York to Los Angeles in 4 minutes. It is the fastest departure speed any spacecraft has ever achieved leaving Earth. But to reach that speed, you need fuel. And here's where the mission almost kills itself before it starts. There is something called the tyranny of the rocket equation. The more fuel you carry, the heavier your spacecraft becomes. The heavier it becomes, the more fuel you need to push that extra weight, and that extra fuel makes it heavier still. It's a spiral, an exponential trap. The relationship between mass and speed is not a straight line. It curves upward violently, and then it breaks the entire premise of the mission. So, how did New Horizons actually do it? It cheated brilliantly. 13 months after launch, New Horizons swung past Jupiter, and it did something almost elegant. It used Jupiter's own gravity like a cosmic slingshot. The planet's enormous gravitational pull yanked the probe forward, accelerating it by an extra 9,000 miles per hour. Zero fuel burned, zero. That speed was stolen directly from Jupiter's own orbital momentum. The planet's orbit was affected by an immeasurable, essentially zero amount. The probe got a free 9,000 miles per hour. That single maneuver shaved 3 years off the journey. Even so, 9 years and 5 months later, New Horizons finally arrived at Pluto, and it blew straight through. No slowing down, no orbit, no landing. It passed within 12,500 miles of the surface at 36,000 miles per hour, and it was gone in a matter of hours. Why couldn't it slow down? Because stopping requires fuel. The same brutal rocket equation that made accelerating so hard makes decelerating just as brutal. Carrying enough fuel to break into Pluto's orbit would have made the spacecraft so heavy it could never have launched in the first place. So the entire mission, 9 years of travel, came down to a few hours of frantic data collection as it screamed past. And there are 2 more problems nobody talks about at that distance: power and communication. At Pluto, the sun is so far away it looks like a very bright star. Solar panels are essentially useless. New Horizons runs on roughly 200 watts of power from a radioactive decay generator. That's less than 2 old incandescent bulbs powering every single instrument, heater, and radio on the spacecraft. And communication? A signal from Pluto takes 4.5 hours one way. Send a message, wait 9 hours for a reply. There's no real-time control. Every command has to be programmed in advance. If something goes wrong out there, the probe handles it alone in the dark at 4 billion miles.
Now, take everything you just learned about reaching Pluto, every challenge, every trick, every compromise, and understand that reaching the nearest star makes all of it look like a warm-up exercise. Proxima Centauri is the closest star to our Sun, 4.24 light-years away. In miles, that is roughly 25 trillion miles away. Pluto is 3.67 billion miles away. Proxima Centauri is 25 trillion miles away.
That is not a little farther. That is approximately 6,800 times farther than the farthest object any spacecraft has ever visited. Voyager 1, right now, is the fastest object humanity has ever launched into deep space. It is traveling at about 38,000 miles per hour. At that speed, it would take roughly 76,000 years to reach Proxima Centauri. 76,000 years. All of recorded human history is about 10,000 years old. The ancient Egyptians built the pyramids 4,500 years ago. Rome rose and fell. Every empire, every war, every scientific revolution in all of human civilization fits inside 10,000 years. Voyager would need more than 7 times that just to reach the nearest star. So conventional rockets are not even worth discussing for interstellar travel. Chemical engines, ion drives, plasma thrusters, they are all beautiful technology, and they all land in the same range of tens of thousands of years. None of them are serious. To reach Proxima Centauri in a time frame that means something, say within a human lifetime, a spacecraft needs to travel at somewhere between 3 and 10% of the speed of light. In miles per hour, that is between 20 million and 67 million miles per hour. We have never come close to that, not even in the same direction. So, what could theoretically work? The first idea is nuclear pulse propulsion. You detonate nuclear bombs behind a massive metal plate. The explosion pushes the plate pushes the spacecraft, repeatedly, hundreds of times per minute. Studies from the 1970s suggested this could reach 12% of the speed of light, putting Proxima about 36 years away. But the engineering required is generations from now. And there is a small additional obstacle: international treaties banning nuclear weapons in space. The second idea is more elegant: a laser sail. Instead of carrying fuel, the spacecraft carries an ultra-thin reflective sail. A giant array of lasers on Earth or in orbit focuses a concentrated beam onto the sail, pushing it behind to extraordinary speeds with no onboard propellant required at all. This is the idea behind a real project called Breakthrough Starshot. The concept is to accelerate probes the size and weight of a postage stamp to 20% of the speed of light. At that speed, the journey to Proxima Centauri takes about 20 years, 4 more years for the signal to travel back. Data from another star system could return to Earth within a single human lifetime. It is genuinely exciting, except for several significant problems. The laser array would need to deliver roughly 100 gigawatts of focused power. Interstellar dust, tiny particles floating in space, would hit the probe at 20% of the speed of light. At that velocity, each particle carries the energy of a small explosion. And the entire communication system, every instrument the probe carries, has to weigh a few grams. None of this is impossible, but none of it exists. And now we get to the part I told you about at the beginning, the part that almost nobody ever mentions, the hardest problem of all. Everything we just talked about, the rocket equation, the laser arrays, the nuclear bombs, all of that is about getting a spacecraft up to speed, about going fast. But what about stopping? In space, there is no friction, none. When a spacecraft reaches cruising speed, it stays at that speed forever with no engines running at all. This is actually useful for long journeys. You burn fuel at the start, coast for decades, burn fuel again at the end. Efficient. But here is the brutal reality. Slowing down at the destination requires exactly as much energy as speeding up in the first place. The deceleration phase is not a bonus problem at the end. It is a full copy of the acceleration problem stacked on top. And under the rocket equation, this does not simply double the required fuel. It squares it. The numbers become so enormous they stop making sense as physical quantities. A spacecraft that can accelerate to 10% of the speed of light would need a catastrophic, mission-destroying amount of additional fuel to decelerate on arrival. The weight alone makes the mission impossible before it begins. The Starshot probes do not have this problem. You know why? Because they are not designed to stop. Those postage stamp probes fly past Proxima Centauri at full speed. They have a few seconds of closest approach, a few seconds to photograph whatever they can. Then they continue outward into interstellar space. Forever. One way. No return. No orbit. No landing. Sound familiar? That is exactly what New Horizons did at Pluto, just farther. Flying past a destination is hard. Actually arriving, slowing down, entering orbit, conducting real science over years, sending a crew, that is a problem of a completely different magnitude. And we do not have a solution. There is one proposed idea: use the destination star itself as a brake, a laser sail running in reverse with the star's own light pressing against the sail from the front as the spacecraft approaches, gently decelerating it without burning any onboard fuel. In theory, it could work. In practice, it has never been demonstrated at any scale, and the precision required is staggering. So here is where we actually are. Pluto took 9 years, a gravity slingshot off Jupiter, 50 years of planning, and still only gave us a few hours. We have never gone back. The farthest object any spacecraft has ever visited is about 4.1 billion miles away. Proxima Centauri is 25 trillion miles away. The gap between those two numbers is so large it almost stops being a gap and starts being a different category of reality. With the most optimistic technology under active research today, we could send a probe the size of a postage stamp. It would arrive in 20 years. It would return data in 25. It would not slow down. It would not orbit. It would not land. And nothing larger, nothing crude, nothing that actually stops. These are not failures of engineering or budget. This is physics. This is the honest, precise, non-negotiable consequence of the distances involved and the laws that govern how matter moves through space. But here's the thing about all of this that I keep coming back to. 20 years ago, we had never visited Pluto at all. We did not know what its surface looked like. We did not know it had mountains made of water ice or a heart-shaped plain the size of Texas. We knew almost nothing. And then we went. 9 years of travel, a few hours of data, and suddenly Pluto had a face. We are somewhere in the middle of this story, not at the beginning, not at the end. We are the generation that figured out the real problems, named them precisely, and started building the tools to solve them. The conversation has already shifted from pure theory to actual engineering proposals with actual funding. The universe does not scale with human expectations. That is not a tragedy. That is the setup. If you want to understand just how vast this really goes, we covered how long it would take to cross the entire Milky Way galaxy and why even the speed of light starts to feel inadequate. Watch that one next. The numbers will permanently change how you see the night sky.